Good evening to one and all present in the conference World Nano 2022. This is Dr. Nagasamy Venkatesh, here to present you one of my research finding titled Atazanavir loaded nanostructured lipid carriers preparation and characterization. So coming to the introduction part of my work, as we know that human immunodeficiency virus, HIV, which is a lentivirus coming under the family of Retroviridae, which is the cause for the development of acute immunodeficiency syndrome, which is also called as AIDS. So according to 2007 update, which is released by the Joint United Nations Program on HIV and AIDS, and as well as in coordination with the WHO, which is published in the AIDS Epidemic Update 2007. Closely 6,800 individuals become newly infected, and over 5,700 patients, that is 5,700 patients, die every year due to this acquired immune deficiency syndrome. Therefore, it is estimated that 33.3 billion persons worldwide are infected with HIV-1, and the developing nations are continue to be the preliminary victims. Moreover, the HIV-infected patients are more vulnerable to the opportunistic infections. Further, abnormal immune responses that are triggered by the HIV infections can also result in other complications, which includes the neurological illness. So my basic aim of the present research is to prepare an Atazanavir loaded nanostructured lipid carriers and characterization of the same. So the outcome or the objectives of this work is to formulate Atazanavir loaded nanostructured lipid carriers, characterization of the developed nanostructured lipid carriers, in vitro dissolution of nanostructured carriers containing Atazanavir, and to enhance the target specificity for the disease management. So the plan of work was carried out in 6 stages. In stage 1, we have carried out a detailed survey on the detailed literature on the nanostructured lipid carriers, the suitable drug candidates for incorporation into the NLC. This is followed by the pre-formulation studies. In pre-formulation studies, we have carried out the melting point analysis, solubility analysis of the selected drug, Atazanavir, preparation of calibration curve, and compatibility studies using differential scanning calorimetry and FTIR. So the third stage is formulation and optimization of the solid lipid nanoparticles. Then the stage 4, we have characterized the solid lipid nanoparticles with regard to entrapment efficiency, drug loading, particle size analysis, zeta potential, and the topography of these solid lipid nanoparticles using scanning electron microscopy technique. Then we have done the evaluation parameters, in vitro release studies of the formulation, different kinetic models to understand the mechanism of drug release from the formulation, and stage 6 is hemocompatibility studies to understand whether the product is compatible with the blood, and this is followed by the in vitro cytotoxicity studies. So pre-formulation studies, we have done the melting point analysis. The theoretical reported melting point is 214 degrees centigrade with regard to the Atazanavir. The practical melting point which we carried out in our lab is 209 degrees centigrade. Then the solid lipid Compritol 888 the theoretical melting point is 69 degrees centigrade. The practical melting point is 72 degrees centigrade. We have also performed the solubility analysis in which the drug Atazanavir shown good solubility in water and as well as in ethanol, but in case of sodium hydroxide solution, it is sparingly soluble. Further, we have developed the calibration curve using phosphate buffer, in which we have developed the linearity between 0 to 50 microgram per ml, and the absorbance increased linearly with the regression coefficient of 0.999. So as I said earlier, we have performed the compatibility studies using two techniques. So the first technique what we have used is our differential scanning calorimetry technique. The differential scanning calorimetry technique is one of the techniques which is widely used to understand the compatibility between the drug and as well as the excipients which are generally used in the study. So what we have done in the study, we have kept the sample in the aluminum pan. We have heated the mixture gradually from 20 degrees centigrade to around 400 degrees centigrade with an increment of 10 degrees centigrade per minute with constant purging of dry nitrogen 50 ml per minute. And we have also kept a blank pan as a reference, and this has revealed is there any incompatibility between the drug and the excipient which are being used. So we have done it for all the excipients which can be seen here, including the formulation also, which I will discuss in the results in the coming slide. And this is followed by the FTIR technique, Fourier transform infrared technique, in which the samples are made as pellet with potassium bromide and they are converted as pellets. So these pellets are kept for scanning from 400 to 4500 centimeter inverse. And these are all the results which we obtained from the FTIR with regard to pure drug, physical mixture, etc. So various functional groups are responsible for certain wave numbers. So the first one is CH stretching, which appeared at the frequency of 3427.62 centimeter inverse. This is with regard to pure drug, whereas in case of physical mixture, it appeared in the region of 3453 centimeter inverse, and this indicates there is no shifting of the peak. Then we have the aromatic CH stretching, in which the pure drug has the wave number of 2955.04 centimeter inverse. In case of physical mixture also, it was in the range of 2915.5 centimeter inverse. This also indicated there is no shifting in the peak. Then C double bond O ketone stretching, which appeared at 1648.23 centimeter inverse. And in case of physical mixture, we got it at 1641.48 centimeter inverse. And the result is no shifting of the peak. In COC stretching carbonyl group, which appeared at the wave number of 1166.01 centimeter inverse. And in case of physical mixture, the peak appeared at the region of 1116.82 centimeter inverse, which indicates there is no shifting of the peak. So all these functional groups which we tested for any incompatibility between the drug and excipients revealed that the drug and as well as the lipid which we used for the study does not have any interaction at all. So next, based on the results which we obtained from the compatibility studies, we have moved on to the formulation aspect of nanostructured lipid carriers. So the nanostructured lipid carriers for the Atazanavir was prepared by solvent evaporation method. And this is the method which we followed for our formulation studies. So in the initial stage, we have taken solid lipid and as well as the liquid lipid, solid lipid and as well as the liquid lipid mixture, the same ratio, and they were subjected for heating process at 70 degrees centigrade. Further, the drug is added to the solid lipid and liquid lipid. So these material constituted the oil phase. Separately, we have taken the different ratio of surfactant in a suitable solvent. We have used water as a solvent or the aqueous phase, and that one is also subjected for heating process at 70 degrees centigrade. Then we have added dropwise of the aqueous phase to the oil phase, which is maintained at the temperature of 70 degrees centigrade. This subsequently formed the pre-emulsion of the formulation, and a stirring process was continued at 2500 RPM using a magnetic stirrer for half an hour. Then this pre-emulsion was further added to 100 ml of cold water, which is maintained at a temperature of 2 to 4 degrees centigrade for the solidification of lipid nanoparticles. So these are all the optimization formulation which we carried out, where the NLCs with same concentration of lipid and surfactant were prepared. So we have prepared around 9 formulations, keeping the drug concentration varying from batch to batch, whereas the solid lipid and the liquid lipid, we kept it as constant over the formulation. And we have also changed the concentration of the surfactant, that is 280, from 0.5% to 2%. And these are all some of the results which we obtained with regard to the entrapment efficiency and as well as the drug loading. So as you can see here, the highest loading of the drug was happened with formulation 5, and it is also supported by the fact that drug loading in this batch also on the higher side, F5. And we have carried out the particle size analyzer using the zeta sizer to find out the particle size of the prepared nano formulation. So it was around some 300 nanometers, and the zeta potential values is also quite good in order to indicate the good stability of the product. So the mean particle size of the Atazanavir loaded NLC was found to be 130 nanometers, whereas the zeta potential value, the charge on the particles, was found to be minus 13.2 millivolt. And we have also received good polydispersity index values, which were found to be 0.27, that is less than 1. It shows the system has narrow distribution, and the zeta potential values is one of the prominent factor to ensure the stability of the formulation. So according to the Nano Technology Characterization Laboratory, the polydispersity index PDA measure of the broadness of the size distribution. As a rule of thumb, the values, PDA values, smaller than about 0.3 considered to be monodisperse and stable formulation. So this is the scanning electron microscopy technique to verify the uniformity of the particle size and shape. And you can see here the particles of the Atazanavir loaded lipid carriers were found to be spherical in shape with a smooth surface. Next, we move on to the in vitro dissolution study. All the 9 batches along with the pure drug were subjected for the in vitro dissolution study over a period of 24 hours. At predetermined time intervals, the samples were withdrawn and they were subjected for the estimation of the drug content using the UV spectrophotometer. So from this we can understand when increasing the concentration of the lipid, the release also decreases exponentially. So this is the in vitro pictorial representation for all the 9 formulation, and from that we have taken F5 batch which has got good entrapment efficiency and as well as the drug loading. So that is also subjected for 24 hours study in comparison with the pure drug. And the data which we obtained from the in vitro dissolution media were plotted into different kinetic models to understand the mechanism of release. So we have used different models. So the first model is zero order kinetics, in which we plotted the cumulative percentage of drug release versus time. The linearity was the R square value was smaller as compared to the first order kinetics, in which log percentage of drug remaining versus time. So our nano formulation follows predominantly first order kinetics. Next, we would like to know whether the release of the drug from the system follows diffusion process or not, in which the cumulative percentage of drug release was plotted against the square root of time. We got the R square value of 0.9, which indicates the prominent mechanism of drug release from the system follows the diffusion time. Further, to understand the mechanism behind the drug release, we have plotted log cumulative percentage of drug release versus log time. This is known as Pepper's model. The earlier one is known as Iguchi model. So we got the n value, that is slope value of 0.464, which indicates the mechanism is diffusion mechanism. Then we have further moved on to another model, that is Hickson-Crowell, where cube root of remaining versus time, that also we got 0.9 value as correlation coefficient. So as I discussed earlier, the release component, the slope value was found to be 0.4648. So the mechanism by which the release happens through non-Fickian diffusion. Then the next one is the hemocompatibility study. So this is done by spectrophotometric analysis by detecting the plasma-free hemoglobin derivatives after subjecting it for incubation with nanoparticles with blood and we'll be separating the undamaged cells by the centrifugation process. So typically, the value of hemocompatibility, which is less than 14%, that is hemolysis less than 14%, is acceptable for the biocompatibility with blood. So the concentration of 125 to 1000 microgram per ml of the formulation were subjected for the hemolysis. In this study, we have used 1% tritoin X 100 was used as a positive control, whereas the saline water was used as the negative control. The positive control showed the percentage hemolysis of 3.714 plus or minus 0.65, whereas the negative control showed the hemolysis of 0.023 plus or minus 0.001. So this is the hemolysis of the optimized batch F5. So this different concentration, despite of increasing the concentration of the material, the hemolysis was found to be same. Then we have performed the Mpt assay to find out the percentage growth inhibition using this formula. So we have used a different concentration of the drug. Initially, we have used the placebo without the drug. The percentage inhibition was 52, 62, 70, and as well as 80, with the IC50 value of 702.54 microgram per ml. Then we have used plain drug, which has the percentage, plain drug in the concentration of 500, 250, 62.5, and 31.25. We have the percentage inhibition of 48.2, 38.45, 29.65, and 19.55, with the IC50 value of 369.6896. Then we have subjected the formulation also for the Mpt assay using 500, 250, 62.5, and 31.25 microgram per ml. The percentage inhibition was 50, 42.55, 27, and 30.5, with the IC50 value of 500 microgram per ml. So this indicates that the formulation is quite good enough to cause the cytotoxicity or the percentage growth inhibition. So this is the pictorial representation for the placebo drug, that is the determination of cytotoxicity by Mpt assay of placebo drug, and this is pure drug, and this is the optimized formulation where you can see the cytotoxicity using the Mpt assay with regard to different formulations. So coming to the summary and conclusion, the selected lipids were found to be compatible with the drug Atazanavir based on the results which we obtained through the FTAR and DSE peach marking method. So study on various formulation variables revealed that all the variables are important. However, the batch prepared using 1:9 solid lipid and liquid lipid with 1% concentration of tween, that is surfactant, showed the minimum particle size with maximum entrapment efficiency and as well as drug loading efficiency. This particular batch F5 was showed entrapment efficiency of 86.39% with drug loading of 7.62%. So the intermittent release studies were performed for all the batches with pure Atazanavir. So the Atazanavir loaded nanolipid formulation from batch 5, that is F5, showed a sustained release of drug over a period of 24 hours. So the best linearity was obtained with regard to the PEPAS model, and chiefly this model represents the drug release either by diffusion, erosion, or swelling, or it may be a combination of diffusion and swelling. And according to the results obtained from the hemocompatibility studies, it showed 14% hemolysis, indicating it was safe towards the RBC lysis. The in vitro cytotoxicity study was performed in vivo cell lines, and the IC50 value of the formulation is about 0.5 mg per ml, and the IC50 value for the drug is about 0.369 mg per ml, which proves that the nanoparticles, when loaded with the drug, shows very less toxicity and it is safe for further studies. So these are all the references with related to the work which we carried out in our laboratory. So to conclude, or the take-home message, the solvent evaporation method was found to be suitable for producing atazanavir loaded nanostructure lipid carriers. Especially the lipophilic drugs like atazanavir can be easily incorporated into the lipid matrix. And this lipid matrix system provides sustained release of a drug for a period of 24 hours. And this can be useful for the treatment of AIDS as compared to pure drug. Thank you for your patient hearing.